Hey everyone, I'm Jordan, the developer of Down Sprite Maker, and today I'm going to be showing you what I think is the coolest feature of my program. First of all, what is Down Sprite Maker? As the name suggests, it's a pixel art character customization program focused on a top-down perspective. Think Stardew Valley, classic Legend of Zelda, or the 2D Pokemon games. When you use the program, there are two phases: customization, where you actually customize your character, and configuration, where you configure what the exported sprite sheet should look like in terms of layout, spacing, and the included animation frames. What sets my program apart from others like it is that it supports multiple sprite styles. What is a sprite style? It's a system that ties together an art style, supported directions, sprite/frame size, animations, and layers. For example, the overworld sprites in the Generation 3 Pokemon games are a different style than the overworld sprites in the Generation 4 games. The art style, size, and in some cases the animations are all different. And not only does Down Sprite Maker support multiple sprite styles, but they aren't hard-coded into the program either. Sprite styles are modules that can be uploaded to the program as zip file archives. That means they can be created, edited, and shared by anyone. In this tutorial, I'll be showing you the step-by-step process of how to produce this sprite style here. It's a simplified version of the Pokemon Generation 4 Overworld sprite style. The head and body have been combined, and there is only a single body type and head shape to choose from. There are a few hairstyles and eye options, and a couple of outfits to choose from. This should hopefully keep the tutorial short and easy to follow, but will still be enough to cover the key program concepts and give you a taste of what is possible beyond this. I'll mostly be covering the scripting, but we'll briefly touch on art as well. As I said, sprite styles are distributed as modules in zip files. In order to be readable by the program, they have to be formatted in a particular way. The only thing a sprite style must contain in order to be readable is a manifest.tds file at root level inside the zip. This is the script file that defines the sprite style. However, you'll almost always want to store the base image assets that the sprite style is composed of in the zip as well as any additional files or resources you want to include for users' consideration. That could be art project files, readmes, whatever you can think of. Manifest.tds is written in DeltaScript, which is a scripting language that I designed and implemented myself. DeltaScript is designed to be very high level, readable, and restrictive. You can't define new types or classes or even call other scripts from within a script. It was designed that way because I wanted it to be the common foundation of domain-specific scripting languages for each of my programs that require one. So each program that uses DeltaScript for scripting, Down Sprite Maker included, then defines its own API that extends the base language with program-specific functionality and data types. The DeltaScript language specification and the Down Sprite Maker API are linked in the description. The API is definitely the more important resource though. You shouldn't have to consult a language spec to follow along or get started. From the root of our zip archive, the base assets for the sprite styles are in the basis subdirectory. Each layer has its own folder. You can see the body asset here. The hair assets match the form of the body asset and can be directly overlaid. You'll notice that for the base assets, skin is green and hair is blue, with slight color variations for highlights and shading. You can even see some skin pixels on some of the hair textures. The eyes are different. These textures do not have the same form as the body and cannot be directly overlaid. We'll see why and how to deal with the difference later. The outfits are also the same form as the body and can be directly overlaid. The outfit textures have multiple color ramps, red, orange, and sometimes yellow, for distinct sections or materials of the garments that have their own recoloring logic. You can make your base assets in the pixel art editor or raster graphics editor of your choice. Sprite, Photoshop, Pixelorama, they're all great choices. I use my own program, Stipple Effect. There are a couple of reasons why. One is preference, familiarity, ergonomics, etc. But the other is how easy it is to iteratively draw and export art in Stipple Effect. If I go into the project file for hair, for example, and I want to add a hairstyle, this is my workflow. Hairstyles are on the hair layer, with the body on the layer below, persisting across frames. Every frame is a different hairstyle. So I make a new frame, draw my hairstyle, and save the project. Now, the issue is that I need each hairstyle option to be its own texture in the hair folder. If I had dozens of hairstyles, individually saving each frame would be a massive pain, right? Luckily, thanks to Stipple Effect's own scripting system, I can automate that process. For each layer with multiple assets to choose from, I set up a save script that has an array of all asset IDs for each of the frames in the project. In our example, that would mean for each hairstyle. In some cases, certain choices will demand special considerations. For example, on our hairstyle layer, we can see that the serene hairstyle has a hairband, an accessory that has its own recoloring logic. This should be represented somehow when the assets are saved, so that it doesn't have to be hard-coded in the script. To deal with this, I define a map in the save script that associates the serene ID with the number 1, representing a one-colored hair accessory. When I run this script from inside Stipple Effect, it extracts each cell on the hair layer and saves it as its own PNG in the hair folder, with its asset ID as its file name. It also concatenates, or chains together, all the asset IDs and any metadata considerations, like the number 1 for the serene hairstyle, and saves them in a .csv, comma-separated values file in the hair folder. Our manifest.tds script will read from these CSV files to determine which textures to read into the program. This way, our art pipeline is entirely separated from the script, and we can add choice options to layers without having to modify manifest.tds. Okay, so let's get started by creating our manifest.tds file. Be sure to name it exactly like this, all lowercase, otherwise it won't be recognized by the program. DeltaScript scripts consist of a header function which has no name because it can't be invoked from within the script body, optionally followed by named helper functions. The header function is always the first function in the script file. For manifest.tds, the header function type signature looks like this. This means the function takes no parameters and returns a style, which is the API type that represents sprite styles. Let's package this together with the base assets in a zip and attempt to upload it to Down Sprite Maker and see what happens. I'm naming the zip style.zip, but feel free to name it whatever you want as long as it has the .zip file extension. When we attempt to upload the style, we are hit with this error screen telling us that the function starting at line 2, column 1, which is our header function, did not return a value even though the interpreter was expecting it to return a style. Let's write our return statement then. Constructors for TDSM-specific data types like style are found in the init namespace. I will bring up the API function definitions for functions that we are calling as we go along. The style constructor takes the arguments ID, which is a string, dims, which is a 2-integer array representing the default pixel width and height of a single sprite/frame in our sprite style, directions, which is an array of strings representing the directions supported by the sprite style, orientation, which is a boolean that indicates whether animations are sequenced horizontally or vertically in our base assets, anims, which is an array of animations supported by our style, and layers, which is a map that maps booleans to lists of layers. I'll explain the purpose and function of each argument as we go along. ID, dims, orientation, and directions are quite trivial, and can be declared as literals, constants, or collections of literals and constants directly in the header function. ID is the unique ID of our style. Down Sprite Maker will only load a single style of a particular ID at a time. If you modify a style and re-upload it to the program with the same ID, the newly uploaded style will override the previously uploaded one. Also, this tilde symbol is just a shorthand in DeltaScript for the keyword final. All it does is declare a variable as immutable. You can usually leave it out, I just personally prefer to write my code that way. By default, a sprite in our style is 32 pixels wide and 32 pixels high. Down Sprite Maker supports a particular set of directions. Styles can either be 4-directional, 6-directional, or 8-directional. And for each of these numbers, the directions supported by the style have to be some permutation, so some ordering, of the specific directions included by each number. Our style is 4-directional. We could just write the directions in as literals, but it's safest to use the constants instead, just in case the literal values corresponding with the directions are changed in a future update. The same thing goes for using the constants orientation instead of true or false. The reason we know our style is oriented horizontally is because, if we look at the underlying base sprite sheets, animations, which orientation refers to, run left to right, while directions run vertically top to bottom. Animations and layers are a bit more involved. These will require helper functions to write in a clean, readable way. For now, we will declare uninitialized variables for each and some useful constants. One of the quirks of DeltaScript is that the outermost scope of the header function is global within the script. That means that a variable declared in the header function, as long as it isn't declared inside an if or a when or a loop, can be referenced in helper functions as long as the helper function is invoked after the variable has been declared. We'll declare global constants for each of our animation IDs, walk, run, and idle. Then we'll get started with our helper functions for defining our animation array and our layer mapping. The reason that the layers of a style are passed to the constructor as a map of booleans to layer lists, instead of just as a simple ordered collection like an array or a list of layers, is because Down Sprite Maker layers have two distinct rules. One is assembly, also called composition, and the other is customization. Assembly and customization are each assigned opposite boolean constants, and each is associated with a list of layers. Assembly or composition layers are the layers that produce image output and are stacked on top of one another to produce the final sprite. Customization layers are the layers that include a choice for users to make, whether it's a color selection, a choice of options for a particular layer like hairstyles, or assigning a numeric value within a range. Assembly and customization layers are not mutually exclusive. Asset choice layers, for example, like the hair, eyes, and outfit layers that will be coming up in our example style, are both assembly and customization layers. A layer's eligibility as an assembly or customization layer comes down to this rule of thumb. If the layer is rendered, i.e. it has image output, it can be an assembly layer. And if the layer allows for any user control or decision to be made manually, it can be a customization layer. Next, we'll define our animations. The animation constructor takes an animation ID, an array of integers representing how many ticks to display each frame for, a frame coordinate function, and a boolean for whether the animation should be played back as a ping-pong animation or in a loop. The number of frames in the animation is implicitly taken from the length of the array. Okay, so let's get a minimum viable product that we can actually upload, compile, and render in Down Sprite Maker. Let's define our body layer. The body layer is an asset layer, not an asset choice layer, because it only consists of a single asset option. The asset layer constructor takes a layer ID, dimensions for sprite sheet slicing, the base asset as an image, a composer, which I'll explain later, and color replacement logic. We'll read in our asset with the readImage function from the DeltaScript base language. Notice how we are using a relative file path that instructs manifest.tds to look for the bases folder in the same directory that manifest.tds itself is located in. Don't worry about this C to init replacement -1 C2 to C2 for now. All that is dummy color replacement logic that does nothing. A composer is a function that takes a sheet, which represents a sprite sheet, as input, and returns a function mapping string input to images. Let's unpack that. All a sprite sheet is an image that has been sliced into individually indexable sprites by dividing it into units of a determined pixel width and height with no remainder. The string to image function returned by a composer serves a specific purpose. The string input is a sprite ID, which is a string that consists of a direction, an animation ID, and frame number all stitched together. Sprite IDs contain all the information to address a particular sprite of a sprite sheet in a sprite style. The image output of a composer's return function represents the rendered content of that layer for that sprite ID. Init default composer is a function that spits out a useful preset composer given your base asset's directions, animations, and orientation information. We'll worry about what exactly it does in a little bit. Let's remove the types that we had temporarily included from the anims and layers arguments of our style constructor and see whether our script compiles now. We'll delete the old zip, repackage our assets, and re-upload. Okay, so that worked. Let's see if we can find any unexpected behavior. First of all, notice that the name of the style in the dropdown is uploaded. We haven't defined any recoloring logic yet, so our preview sprite has the same green skin from the body asset file. Okay, the idle animation is displaying the wrong frame, and the character turning isn't working properly either. The character isn't turning 90 degrees counterclockwise like it's supposed to. Let's see what we can do about that. First things first, the order in which the directions are defined actually matters, or at least it does if we are using the default composer. The reason the character turning wasn't working properly is because the order of our directions array, north, west, south, east, doesn't match our base asset sprite sheets. In our sprite sheets, the order of our directions is south, west, east, north. The default composer uses the direction ordering, orientation, and animation frame coordinate function to know where each sprite is located in the base asset sprite sheets. Secondly, the reason the idle and run animations weren't recognized properly is because we didn't pass in their initial coordinates to init simple frame coord func. Simple frame coord func is similar to default composer in the sense that both are useful presets that make assumptions about the layout of the base asset sprite sheets. You can choose to define your own composer and frame coordinate logic, and there are situations where you may have to. The idle animation is a single frame at 1,0 in the sprite sheet, which reuses the in-between frame from the walk animation, and the run animation starts at the frame coordinate 3,0. Re-uploading to TDSM with our changes shows that we resolved both bugs. Let's have a look at the special metadata functions that Down Sprite Maker checks for in manifest.tds. These are name, info, settings, and preview scale. None of the metadata functions take any parameters. They have to be named exactly to be recognized by the program. Users should assume that they are called by the interpreter in an isolated execution context, so they also shouldn't reference any global variables declared in the header function. Name returns a string that will be displayed as the sprite style name in the sprite style selection dropdown. User returns a string that will be shown as the tooltip message when the user hovers the mouse over the help icon next to the sprite style dropdown while the sprite style is selected. Let's leave settings as an empty array for now. I might make a follow-up video going through settings at some point, but it's not relevant right now. Let's set preview scale to 1 for now and repackage our zip. When we upload the updated zip, we see that the name is displayed in the dropdown and the info message is displayed as the tooltip on hover. However, you'll notice that the preview sprite is suddenly much smaller. That's because it's now being rendered at 1x scale. By default, the preview scale is 2x. 2x is ideal for 16-bit sprites and the most common scales of pixel art sprites. However, if you're working with more detailed sprites on a larger canvas, you may want a 1x preview scale. Or if you're working with extremely small sprites, you may want a 3x or even 4x preview scale. Let's set the preview scale back to 2 and quickly recompile the style before we move on. Let's get the hair rendering next. This is our first asset choice layer. If you recall from the recommended art workflow explanation, our basis folder has subfolders for each assembly layer. Body is a single asset, but hair, eyes, and outfit each have several options to choose from. Each of those layer folders has each of its options saved in a separate PNG image file, along with a CSV file of all the possible options. The getAsset function takes a layer ID and an asset ID and reads the corresponding asset from its PNG file into the program. I'm going to go ahead and map out a few functions that we'll need in this step. Replace end cells, and RBG only are color replacement functions. RBG only is a utility function that strips out a potential non-opaque alpha value from a color and returns its opaque equivalent. Replace is a special case of replace end cells with 0 specific color selections. That will make more sense later. GetChoices takes a layer ID and a post-split function to produce an array of asset choices for a particular layer. It reads the CSV file corresponding to its layer ID and then splits the file into its entries by splitting the file contents at every comma. It determines how many asset choices, represented by n, to reserve in its returned array by taking the length of the split array. Then, for every index in the asset choices array, it calls the post-split function on the CSV entry at the same index. Call is a special DeltaScript function that can be called on function references to invoke their function with a set of arguments. The post-split func parameter is a function reference of the type string to asset choice. HairSplit is one of the functions we will be passing to getChoices as an argument for the post-split func parameter. You can see the type signature of hairSplit matches the functional type of post-split func, a single parameter of type string and returning an asset choice. Now would be a good time to explain what an asset choice is in terms of data. The asset choice type represents a blueprint for a selection option of an asset choice layer. It consists of an asset ID, which should be unique among the asset choices of any given asset choice layer, color replacement logic, and an array of color selections specific to the asset choice that can be indexed by the color replacement logic. In hairSplit, we split our CSV entry with the colon. If the split operation resulted in 2 sections, and the second section, i.e. the section to the right of the colon, can be cast to an integer equal to 1, we return an asset choice that uses the first section as the asset ID and uses the function replace end cells with the number of selections argument of 1 for its color replacement. We'll worry about the color selections it applies to the asset choice constructor later. Only the serene haircut in our example will match this condition, but we'll write it in an agnostic way to make it extensible. Like I said in the art workflow section, this way we'll be able to add hairstyles without having to modify manifest.tds in the future. If our condition isn't met, we assume that the CSV entry has no colon character, and the entire entry is supplied to the asset choice constructor as the asset ID, with replace as the color replacement function. Let's quickly refactor our body layer definition to use the getAsset function. Now we move on to the hair layer definition. The asset choice layer constructor takes a layer ID, dimensions for sprite sheet slicing, an asset fetcher function, an array of asset choices, a no choice configuration, a composer, and a 2-integer array representing the preview coordinates. The asset fetcher function is of type string to image. It takes as input an arbitrary asset ID and returns the base asset for that asset ID. To determine the hair layer's array of asset choices, we use our getChoices function with the hair layer ID and hairSplit function as arguments. The double colon is the function reference operator. You can use it followed by the name of a helper function to create a reference to that function. A no choice configuration tells an asset layer how to deal with the possibility of no choice as an option. We'll explore that in more detail later. For now, we'll use the no choice equal configuration. The preview coordinate tells the asset choice layer at which XY coordinate in its asset choices sprite sheets to find the frame that should be used to preview the asset in the user interface. Next, I'm going to define a bunch of constants related to color. I'm not going to go into a lot of detail here, except to point out that DeltaScript supports 6 and 8-digit hex color literals, so you can define RGB and RGBA colors very easily. It also has the RGB and RGBA functions to create colors, and the TDSM API also adds an HSV, so hue, saturation, value, color constructor in the color proc namespace.
These color constants under the colors section comment are the colors that match the exact colors used in the base assets for skin, hair, eyes, and outfits. Then on the other hand, the constants in the swatches section are the preset color options that will pop up for the various color selections we will implement. These are defined in the header function so that they are global variables that can be referenced anywhere. Our first color selection, which is a data type different from a color itself, representing a place where a color can be assigned, is hair ac col, or hair accessory color. This is the color selection we're going to supply to the asset choice for the serene hairstyle. I'll also be skimming over the actual color replacement logic, which is the body of the replace end cells function. The variable input represents an arbitrary pixel color that is sampled from a base asset. The role of the color replacement logic is to determine, for any pixel input color, which color selection should be responsible for its recoloring, and how the color assigned to the color replacement should be transformed to produce the final output color. In our example, we start by defining several Boolean variables that determine whether our opaque input color matches colors found in any of our color sets for skin, skin outline, hair, or the eye/iris color. If a color match is found, the index and b, our base color variables, are set to the corresponding values. If no match is found, the index remains -1. An index of -1 means that no recoloring takes place and the input pixel is propagated to the output. We'll leave it to do comment for now that we'll return to when it comes time to implement color replacements for clothes. Replace end cells then returns a color replacement that takes the index and a color transformation function that does some color math to apply some highlights or shading to the color yielded by the indexed color selection. We have to remember to add our hair layer to both our assembly and customization layer lists. If you recall, asset choice layers are valid as both assembly and customization layers because they produce rendered output and they allow for user choice. Okay, now let's repackage our zip and see where we're at. We can see our hair layer in our customization panel, and the hairstyles are being rendered on top of the body correctly, but we have no color replacement happening. To fix that, we'll define a couple of color selections for skin and for hair. The color selection constructor takes a name, which is displayed in the program user interface above the color assignment button, a Boolean, and an array of colors called swatches. The Boolean represents whether any RGB color can be assigned to the color selection, or whether it must choose from amongst its swatches. Whether it can be assigned to any color or not, a color selection is randomly assigned to one of its swatches when it is randomized. Now that we have our color selections, we have to add them as influences to the corresponding layers. This does two things. One, it allows the color replacement logic to access the color selections when it is indexing into the layers influencing color selections. And two, it will cause the layer to dynamically re-render its output whenever one of its influencing color selections updates its value. You may be wondering why I'm adding the skin tone selection as an influence to the hair layer along with the hair color selection. If you recall, some of the hair layer base asset choices have green skin pixels on them. This is to override the skin shading on the body layer below. We also need a way to access and reassign our color selections. Let's define a color selection layer to house them. The color selection layer constructor takes a layer ID and an array of color selections. We'll add it to our customization layer list. You might be thinking that because it has to do with color and visuals, that the color selection layer should be an assembly layer as well. However, it doesn't produce rendered output, so it isn't. The values assigned to the color selections in the layer will influence our sprite output, but the layer doesn't itself produce an image. Let's recompile this and see whether it works as expected. The positives are that our color selection layer is here. The color selections display the expected swatches to choose from, and they can be assigned successfully. Hair is working as expected, but the skin is still green. The reason why is because we're still using our dummy placeholder function that does nothing as the color replacement in our body layer definition. Let's replace it with a reference to replace. Repackage, re-upload, and that works exactly as expected. Nice. Although the hairband recoloring still doesn't work for the serene hairstyle. Let's go back to the to-do comment that we left in replace end cells and add the clothing check section to the color replacement logic. If we're dealing with clothing, we know our parameter n is positive, i.e. greater than 0. N represents the number of unique clothing color ramps, at most 3, red, orange, and yellow, that are present in the asset undergoing color replacement. We'll use a loop to check for our opaque input color in each of the first n color ramps. If a match is found, like for the skin, hair, and eye checks, the index and base color variables are reassigned. And there we go, the hairband can now be recolored as well.
Let's get started with the eyes. These present a unique challenge though. As I said in the art section, the eye base assets are not the same form as the body assets and can't be directly overlaid like the hair assets were. That means we can't use the default composer. We have to define a bespoke composer instead. We start by defining color selections for eye color and eyebrow color. It's worth mentioning that we could use the hair color selection to recolor the eyebrows. A separate one gives us more customization options, but it's just a matter of personal preference. Our eyes layer definition is quite similar to the hair layer definition. One difference is that because the eyes layer has no special case like the hair layer did with the Serene hairstyle that had a hairband, we don't have to define a complex post-split function for get choices. Instead, we can just inline an anonymous function that assigns the entire CSV entry as the asset ID and uses replace as the color replacement logic. Another difference is that instead of using noChoice equal for the noChoice configuration, we can use the noChoice probability constructor with an argument of 0.0. We'll touch on that in a bit. And for now, we'll use the default composer as a placeholder. Some eye options include skin and eyebrow pixels, so we add the color selections for skin, hair, and eye color as influences for our eyes layer. Again, eyes is an asset choice layer, so we add it to both the assembly and construction layer lists. Let's see what this produces in Down Sprite Maker. Everything that we expected to find is in the customization panel and works as expected. The issue is that the eyes aren't overlaid onto the body in a way that makes sense. This is where our bespoke composer comes in. As discussed, a composer is a function that takes a sprite sheet as input and returns a function that returns images given sprite ID strings. Our bespoke composer, composeEyes, is a function with this type signature. We will pass a reference to this function to our eyes asset choice layer constructor that will replace the default composer. Our function body is a single return statement that defines the function returned by the composer. Given a sprite ID, we need to extract the relevant information to know which frame of our eyes base asset image to query in the sprite sheet. Each eyes base asset image is a 4-frame sprite sheet where each frame shows the eyes facing in a different direction. The north-facing frame can be ignored as the eyes aren't visible in that case. The directions are sequenced in the same order as they are for the body, hair, and outfit assets, and the same order of the elements in our directions array in the script. The only relevant information we need to know which frame of the sprite sheet to query is the direction of a particular sprite ID. We can extract each component of the sprite ID, the direction, the animation ID, and the frame number by using the API utility functions extract direction, extract anim ID, and extract frame. Let's define an image variable content that we'll use to return our final image content for our layer. We'll use the new image constructor from the DeltaScript base language and pass it a pixel width and height from our dims array. I prefer using the constants to index into dims, but this is the same as typing dims0 and dims1. Next, we'll define another image variable sprite to store the eyes frame corresponding to the direction component of our sprite ID. Once we have our sprite, we'll need to calculate any necessary X and/or Y offsets due to the animation or animation frame, and then draw our sprite onto the content image with the calculated X and Y offsets. Let's ignore the offsets for now. To calculate our desired X frame coordinate, we'll define the helper function headX and loop through the directions array until we find a match and then return the index. Let's replace the default composer with a reference to composeEyes and test it. Okay, first of all, the style should initially be loaded with an eye selection made, even if we want noChoice to be a valid option if we want users to be able to make eyeless sprites. The good thing is that now we can see that we are displaying the correct eyes frame for each direction, regardless of the animation or frame. However, we can see that because we skipped over the offsets, the eyes remain fixed in place, even as the head bobs as part of the walking animation. Let's quickly address the style loading with no eye selected. All we have to do is add a single statement after the eyes layer has been initialized. Eyes.choose0. What this does is it explicitly assigns the eyes layer its first asset choice. Now we can see that we load with the first asset choice selected even though noChoice is still a listed option. If I click the die to randomize the layer, it chooses an asset choice at random. No matter how many times I click it, it won't select noChoice. The reason for that is that our noChoice configuration is noChoiceProb0, which defines noChoice as a valid selection possibility but assigns a probability of 0% of it being assigned by randomization. Another way to ensure that the style loads with an eyes asset choice selected is by defining the layer with noChoice invalid. When we compile this, we see that unlike the hair layer, we can't even select noChoice for the eyes anymore. Now, just to see, if we were to define the eyes layer with noChoiceProb1, noChoice would have a 100% chance of being selected by randomization. Let's quickly confirm that's the case. Yep, every time I click randomize, noChoice layer chooses no selection. What we did on the hair layer is define the noChoice configuration with noChoice equal. Rather than a custom probability of random assignment, this gives noChoice the same probability of random assignment as each of the asset choices. So for a layer with 7 asset choices, noChoice equal gives noChoice, as well as each of the other asset choices, a 12.5% random assignment probability, because there are 8 valid selection options. Next, we have the X and Y offsets for the eyes. This is where the other sprite ID components, animation ID and animation frame number, come in. Instead of a switch statement, DeltaScript has its own control flow structure called when. When has 3 types of non-trivial cases, and an optional remainder case marked by the keyword otherwise. The simplest case type is the is case, which simply performs an equality check on the control expression and the case expression. Is cases can have multiple case expressions separated by commas, and as long as one is equal to the control expression, the case is passed. Once the case passes and its body is executed, the control flow drops out of the when statement and doesn't check the following cases. There are also matches and passes cases. We'll see matches later on, and I might cover passes in a DeltaScript deep dive video at some point. The arithmetic in these offset assignments might look somewhat convoluted, but I wrote it this way to avoid having to nest conditionals that perform checks on the animation frame. The offset Y assignment in the is AID walk case is responsible for the 1 pixel upwards displacement on frames 0 and 2 of the walk animation, which are the frames where the character is taking a step. The run animation requires a nested conditional for each direction because the offset logic is too different in each of the 3 non-trivial directions to reconcile on a single readable assignment for X and Y each. We'll come back to this to add an eye height that we can modulate, but let's test it for now. Okay, looks good. It's really coming together. We can see the eyes bobbing up and down when the character is walking and moving from side to side and front and back when the character is running. Down Sprite Maker also supports math layers, which we can operate on to modulate things. We're going to use eye height as a use case example. Let's make our eye height layer. The math layer constructor takes a layer ID, a minimum integer value, maximum integer value, default value from within the range inclusive, and a formatting function of type int to string whose job it is to produce string output for every possible value of the layer. The string output is then displayed by the user interface as a description of the math layer's current value. We're defining eye height to range between -1 and 1. We'll call a value of 1 high, 0 average, and -1 low. Back in compose eyes, our bespoke composer for the eyes layer, we'll add a single decrementation assignment statement that decrements the Y offset by the current value of the eyes height layer. Just quickly, I want to point out that we can reference the eye height layer in compose eyes because we defined it in the header function, so it's in global scope. Let's also not forget to add eye height to our customization layers list. Repackaging and re-uploading this, we can see that we can move the eyes up and down within a 2 pixel range centered on average now. What I have now is actually what I want, but let me just experiment a bit. I'll increase the range from -5 to 5 and use the when statement to define the format function. I'll keep the high, average, and low labels, but now every positive value will be marked high and every negative value will be marked low. To achieve that concisely, I'll use a matches case statement in when, which uses the special identifier underscore as a stand-in for the control expression. Let's test that out just to see. Yeah, now we can increment and decrement the eyes much higher and lower. The last thing I'm going to cover is outfits. If you've been following along, then you should know roughly what the approach here is going to be. Firstly, I'm going to define an array of 3 color selections for the maximum of 3 color ramps, red, orange, and yellow, that are present on the outfit base assets. The outfit layer is an asset choice layer, as you probably guessed. Almost everything in our constructor has already been covered. We can use the default composer here as well because the outfit base assets can be directly overlaid on the body base asset. The only thing that's different is that we need a unique post-split function to pass to get choices. Our post-split function, outfit split, is quite similar to hair split from earlier. The difference here is that outfit CSV entries always include a colon with either a 2 or a 3 associated with the outfit. In the case of a 2, we return an asset choice with the first 2 elements of the outfit call's color selection array. In the case of a 3, we pass the entire 3-element array to the asset choice constructor. Looks like we're ready to upload. Moment of truth, and it works. Okay, for extra credit, I'm going to make one more adjustment. The sprite style already has all of the customization options we want and works perfectly, but it can still be improved. One of my favorite workflows in my program is to hit randomize until I see something I like, lock it in, and keep randomizing until I can make the final adjustments to my character manually. Our issue is that we have all our color selections on the colors layer. If we randomize that layer, every single color selection is randomized. That means we lose the individual control over skin color, hair color, and eye color if we're doing style level randomization, because we can't lock individual color selections. The solution is to split the color selections into distinct color selection layers. Those are relatively trivial code changes to make. Let's make sure not to forget to add our new color selection layers to the customization layer list and recompile the style. Yep, now our color selections are split into 3 distinct color selection layers. The functionality is still the same, but now, when we want to do a style level randomization by clicking the die in the top right corner, we can lock particular color selections whose assigned colors we want to preserve. I've locked the skin color, hairstyle, and eye height. Let's hit randomize a few times. You can see the hair color, eye shape and color, and outfit all changing, but the values of the locked layers persist across the randomizations. And I think that's probably a good place to stop. There's a few things that I would point out about this that you would probably want to change. For example, with the north/up facing sprites, long hairstyles can get clipped by the outfit when they should actually be rendered above them. That's something you could fix with dependent layers or composed layers, which I didn't cover. There are also mask layers, which let you do things like this, where you can clip hair under a hat. Choice layers, which are text selections that can be operated on similarly to how we operated on math layers with eye height. Then there are advanced techniques and concepts like decision layers, group layers, or choice syncing. I might make a follow-up to this video at some point covering those, but they are all documented in the API for anyone interested, and there are sprite styles that are freely available that utilize them. All of the resources in the tutorial are linked in the description. You can read the full API specification, complete with guides and theory pages, on GitHub. There's also a sprite style development guide available on itch.io if you want to follow along with this tutorial or see more advanced sprite style examples and techniques. You can download the Down Sprite Maker VS Code extension from the extensions marketplace for script syntax highlighting. Please like the video if you found it helpful and consider subscribing to the channel for more Down Sprite Maker content, as well as videos about my other programs and future projects. You can buy Down Sprite Maker on itch.io. If you've bought the program and are getting a lot of value out of it, please consider rating or reviewing it. It helps me out a lot and will help the program reach more people. Approved sprite styles can be found in this collection on itch.io. They've either been made by me or are made by members of the community and verified by me. If you're interested in having your sprite style added to the approved collection, upload it to itch.io and post a link to it in the GitHub discussion board. Make sure you have the rights to distribute the assets that comprise your sprite style. If all of the art is original, you can sell the sprite style. If not, please make sure that you're distributing it as a free download. If you're a pixel artist who's interested in making a sprite style for TDSM, but you aren't comfortable writing the code for the script, I'm launching a commission service on Ko-fi where you can give me your base assets and I will write the script for you and deliver a working sprite style. If you're interested in that, the link is in the description. And that's all from me for now.